Well, we have completed our look at background material and preliminary material, an in-depth look at equivalence relations as it relates to canonical forms and so on. Before we start linear algebra proper, however, we need to cover a little more ground. And the first item of business is cardinality. This is not going to come up terribly often during this course, but it will come up a few key times, and so it's worth taking a look at this material now. I've shortened it quite a bit, and it's good to know this in any case if you're a math major or going to continue your studies in mathematics. This material is worth at least some familiarity with. Informally speaking, to every set A, there is associated an object, actually another set, called the cardinality or cardinal number of A. And there's two common notations. One is vertical bars around the set. The other is CARD of A. And there are other notations. The cardinality of a set is intended to describe its size. The cardinality of a finite set is just a natural number. And no surprises there. It's just the number of elements in the set. The theory of infinite cardinal numbers, which are also called transfinite numbers or cardinal numbers, was developed by the German mathematician Georg Cantor around in the late 1800s, early 1900s. Cantor's theory of cardinal numbers was initially regarded as extremely counterintuitive and in fact engendered severe criticism from a variety of sources. Some philosophers, some theologians, also some famous mathematicians, in particular Leopold Kronecker. You may have heard of the Kronecker delta function, and Henri Poincaré, who was a very famous mathematician. Kronecker referred to Cantor in public as a scientific charlatan and a corrupter of youth, of all things, for his theory of infinite or transfinite cardinals. Actually, Cantor himself believed that his theory had been communicated to him by God, although many devout Christian theologians believed it to be heresy. So it has a very colorful history. But fortunately, the passage of time has restored reason, and in 1904, the Royal Society awarded Cantor its Sylvester Medal, which is the Society's highest mathematical honor. And the famous mathematician David Hilbert, you may have heard of Hilbert spaces, defended Cantor's theory and declared, "No one shall expel us from the paradise that Cantor has created." Well, anyway, the history notwithstanding, let's take a look very briefly at Cantor's theory of transfinite cardinal numbers. It turns out that it's easier to define what it means for two sets to have the same size or the same cardinality than it is to actually define what a cardinal number is. That is going to be, unfortunately, a bit beyond our intentions here. I did do, I think it's 4 lectures on YouTube. The last 4 of my transition to advanced mathematics lectures is devoted to cardinality, and that's a much deeper look than we're going to do here. So if you're interested in more information about cardinal numbers, you can look there. And there are notes that accompany those lectures as well. So, 2 sets, S and T, are said to be equipotent, also called equipolant or equinumerous. And I'll write it this way with the tilde sign. If there is a bijective function between the 2 sets, also called a one-to-one correspondence. And as we will see, 2 sets have the same cardinality if and only if they are equipotent. I'm not going to give proofs in these notes. There are proofs in the transition notes that I just mentioned. And of course you can find this material in textbooks, and you can Google and probably find other sources as well. But I'm just going to give you the highlights without proofs. It is possible to show that the natural numbers, which are the numbers 0, 1, 2, 3, and so on, natural numbers do include 0, are equipolant to the integers, which at first glance would seem to be a much larger set, because the natural numbers don't include the negative natural numbers. Yet these 2 sets are equipolant and therefore have the same size. Similarly, the natural numbers and the rational numbers are equipolant and therefore have the same size or cardinality. Maybe you can begin to see here why some people were initially a bit upset about this whole theory. That is, in some sense, rather counterintuitive. But it does follow, both these statements follow from the definition. There is a bijection between n and z, and there is a bijection between n and q. So, as I mentioned, to give a formal definition of cardinal number would just take us too far away from the purpose of this book. We'd need too much background, it would take too long. So we'll just go for an informal definition. And it goes something like this. This is very informal. If V denotes the collection of all sets, I can't call it a set of sets. There are paradoxes that would result in that, so I have to use the term collection of all sets. Then equipotence is an equivalence relation on V. And so it partitions V into equivalence classes. Everything in an equivalence class is equipolant to everything else. And 2 sets that belong to different equivalence classes are not equipolant. Now, in each equivalence class, we can identify a unique, very special set. And this is where I have to just beg your indulgence, because I can't tell you how that set is identified. But it is called a cardinal number. It's defined by certain properties that we just can't go into at this time. Nevertheless, the collection of cardinal numbers then forms a system of distinct representatives for equipotence or equipolence. I'm using both terms. I have this tendency to go back and forth between the two, and I don't know why, but they mean the same thing. Okay. So every set, then, since every set belongs to a single equivalence class, is equipotent to a unique cardinal number. And that is known as the cardinality of the set. Every natural number is a cardinal number. Also, the set of all natural numbers is itself a cardinal number. Cardinal numbers are sets. Virtually everything in mathematics is a set, one way or another, even though it doesn't look like it. Natural numbers are sets, matrices are sets, functions are sets. Almost everything we can define, or that we do define and use, is a set. There are some exceptions. For example, the collection of all sets is not a set. But again, that would take us a bit off course here to go into that in detail. But the natural numbers are cardinal numbers, and so is the set of all natural numbers. And when that set is thought of as a cardinal number, it is denoted by this symbol. This symbol that looks like a fancy N is read Aleph, A-L-E-P-H, and it's the first letter in several Semitic alphabets. When we put a subscript 0, we read this Aleph-null. So the natural numbers are the set of natural numbers is in fact this cardinal number. And so anything equipolant to the natural numbers has this cardinality. So the natural numbers themselves, the integers, the rational numbers, all have cardinality Aleph-null. And it turns out that Aleph-null is the smallest infinite cardinal. So these three sets have the smallest size among all infinite sets. The real numbers, on the other hand, do not have cardinality Aleph-null. They have a bigger cardinality, strictly larger. It's denoted by the letter C because it's called the power of the continuum. And sometimes the real line is referred to as the continuum, so that's where that terminology comes from. It's not the Q continuum of Star Trek, just to be clear. My guess is that nobody who writes Star Trek or acts in it knows what the power of the continuum really is. But I'm digressing. A set is finite and has cardinality K if it is equipotent to a set, to this particular set 1 through K. Okay. So this is probably not major news here. This is a finite set. Anything in one-to-one correspondence with this set is finite and will have K elements. A set that's not finite, of course, is called infinite. The sets with cardinality Aleph-null, so these are three examples here, are said to be countably infinite. And any set that's either finite or countably infinite, again, that's the smallest infinity, are said to be countable sets. So countable sets include two types, the finite sets and the countably infinite sets. Any infinite set that's not countable is said to be uncountable. So the real numbers, the set of real numbers, is uncountable. The sets of natural numbers, integers, and rational numbers are countable. The irrational numbers are uncountable. So in a very loose sense, but in an accurate sense, there are as many irrational numbers as there are real numbers, but far fewer rational numbers than real numbers. So when you split the real numbers, when you partition it into the rational and the irrational numbers, the rational numbers, while infinite in size, are much smaller than the set of irrational numbers. In very loose terms, there are a lot more irrational numbers than there are rational numbers. Cardinal numbers can be ordered. If S is equipotent to a subset of T, we would write cardinality of S less than or equal to cardinality of T. There is an issue here, and that is what happens if you replace S by a different set and T by a different set, but S is still, the new set, let's say S prime, is equipotent to a subset of T prime. The cardinalities of S and S prime are the same if S and S prime are equipotent. Same thing for the cardinalities of T and T prime, but do we still have this less than or equal to? So there's an ambiguity here, a potential problem, and that is this seems to depend on which sets you pick, S and T, but in fact it does not. If S is equipotent to a proper subset of T, but not equipotent to all of T, then we can put a strictly less than symbol here. And that second condition, not saying not all of T, is critical, because the natural numbers, for example, are a proper subset of the integers, so they're obviously equipotent to a proper subset of the integers to themselves, but they're also equipotent to the entire set of integers. So the cardinality of the natural numbers is not less than the cardinality of the integers because the two are equipotent, even though n is also equipotent to a proper subset of z. Okay, so this gets a little tricky. Some of the basic properties of cardinal numbers are analogs of the corresponding familiar facts for finite cardinal numbers, the natural numbers. But some are not. Some are rather strange and new and different, as we'll see in a minute. As far as being similar, if S and T are finite sets, then of course if the size of S is less than or equal to the size of T, and the size of T is less than or equal to the size of S, then the two sets have the same size. That also holds for infinite sets. But the proof is a little bit more difficult than it would be for finite sets. Also, if S is a set of finite cardinality, say n, then the cardinality of the power set of S is 2 to the n. In other words, there are 2 to the n subsets of a set of size n. So, in particular, the cardinality of the power set of a finite set is strictly greater than the cardinality of the set. This is also true for infinite for sets of infinite cardinality. We have this relationship for all sets. Cardinality of S strictly less than cardinality of power set of S. On the other hand, for infinite sets, but not for finite sets, the collection, which I denote by P sub 0 of S, of all finite subsets of S, actually has the same size as S. This is something that will come up, I think, only once in the book. Okay, so here's a little summary. This statement about cardinalities, if cardinality of S is less than or equal to cardinality of T, and cardinality of T is less than or equal to cardinality of S, then the two cardinalities are equal. That's called the Schroeder-Bernstein theorem, or sometimes the Cantor-Schroeder-Bernstein theorem. The statement that the cardinality of a set is strictly less than the cardinality of its power set is known as Cantor's theorem. And then here's a repeat of this fact I mentioned just a minute ago. To my knowledge, that doesn't have a name. Cantor's theorem, though, shows us something quite remarkable. We can start with a set, and let's say we start with the natural numbers. Take its cardinality, Aleph-null. Take the power set of the natural numbers, that has bigger cardinality. Take its power set, we get yet a larger cardinality. And this we may continue indefinitely. And so there are infinitely many different infinite cardinal numbers. Let's take a quick peek at the arithmetic of cardinal numbers. It is possible to define the sum, the product, and a power of cardinal numbers. And this is how it's done. If we have two cardinal numbers, kappa and lambda, and if S and T are disjoint sets, S has cardinality kappa and T has cardinality lambda, then the sum, kappa plus lambda, is defined to be the cardinality of the union. The sets must be disjoint for this. The product, kappa times lambda, is the cardinal number of the Cartesian product. The power, kappa to the power lambda, is the cardinal number of the set of functions from T to S. This is a common notation for functions from T to S. Well, we won't go into the details on why these definitions make sense. They do seem, for example, to depend on which sets you pick, but they in fact do not. So they are well-defined concepts. Cardinal arithmetic is also, in some ways, relatively well-behaved. It's associative, both operations are commutative. There is a distributive law, and the, dare I say it, the usual properties of exponents hold. But there are, as I said before, ways in which cardinal numbers behave rather strangely. One of which is that if you have two cardinal numbers, at least one of which is infinite, their sum is equal to their product, and that is equal to the larger of the two. So there's a kind of absorption going on. If you have two cardinal numbers of different sizes, infinite, at least one being infinite, so the larger one. If you add the two together, adding the smaller cardinal to the larger cardinal does nothing. Similarly for multiplication. So this is a little strange. Here's another fact about finite sets. Let's say you had a family of k finite sets, each of which has size at most n. Then the union of the sets will have size at most k times n. If you've got 10 sets, each of which has size at most 5, throw them all together, the union has size at most 10 times 5, 50. Maybe less, but that's the largest it can be. Same thing for, here we have a collection of kappa sets. So the size of the index set is the cardinal number kappa. And if each set has, its cardinality is bounded by lambda, then the cardinality of the union is less than or equal to lambda times kappa. So it's the analog for finite sets. Finally, we have a result that we will use in the text once or twice maybe, I can't remember. So let's look at that. I said already that this notation, y to the x, when y and x are sets, this is the set of all functions from x to y. Suppose we have a function from x to y, and suppose that 0 belongs to the codomain y. Then we can define the support of the function to be the set of all elements of the domain x that get mapped to a non-zero element of the codomain. So here it is in symbols. The support of f is the set of all elements little x in the domain such that f of x is not 0. Now, let x be an infinite set and let f be a countable set. So f is either finite or countably infinite. But we want it to have size at least 2. Then the set of all functions from x to f has cardinality greater than that of x. But assuming f contains 0, this set, which I just subscripted 0 here, of all functions from x to f that have finite support actually has the same cardinality as x. So in loose terms, if you're only considering functions that are non-zero at a finite number of places, then you get a much smaller set than the set of all functions, so much smaller that it actually has size equal to the size of the domain. And so in particular, and this is what we're going to need in the text, the size or cardinality of the set of all functions from x to f with finite support is strictly less than the cardinality of the set of all functions. And that should do it for cardinality.